Good afternoon and welcome to lecture number 9 in Introduction to Economics. And today's topic of my lecture video is applications of dummy independent variables. Again, this video is dedicated to Dr. Bilwan of HKBU. He has done a lot of efforts in preparing these slides. So this video is dedicated to him. Let me start with the qualitative information. By dummy variable, we mean that sometimes the variable cannot be quantitative, but it will be qualitative, like gender, male and female, size, small, medium and large, zone like east, south, west, north, center, and similarly time period, maybe peace time or war time, and similarly before the crisis time and after the crisis. We can also classify age as young, middle and elder, and we can also classify level of education as elementary, high, college and postgraduate, and maybe other variables. And in that case there is no other quantification of zone like east, south, west and north, but we can just give them code like d1 is equal to 1 if east 0 otherwise, d2 is equal to 1 if south 0 otherwise, and so on. Similarly, d1 is equal to young, and if d1 is equal to 1 if the person is young and 0 otherwise, d2 is equal to 1 if the person is of middle age and 0 otherwise. Here is an example of a gender issue of whether discrimination is existing for salary. We have 25 observations. These are number of observations. This is male dummy. 1 stands for male and 0 stands for female. Similarly, this is a female dummy. Here it is 1, so male. Here it is 0. Here it is 1 female, and here it is 0. And this is salary in thousands, and this is year of teaching experience. So we have 3 variables. One is our salary. This is our dependent variables. This is our independent variables, which is quantitative, and we will use one dummy variable for gender. Now if we separate this sample by male and female, let us suppose this is the separate sample of male, and we have 1 2 3 4 5 6 7 8 9 10 11 12. There are 12 observations, and this is the starting salary, and this is the x2 variable, which is years of teaching experience. And this example is available in Gujarati book in 95 edition, and the table number is 15.1 and 15.5. so the total number of observation is 12, and this is a separate sample for females. These are 13 observations, and again this example is in Gujarati. So this is the starting salary in thousands. This is dependent variable y, and this is our independent variable, and that is years of teaching, and it is denoted by x2. Let us suppose this is the estimated regression for the male teachers. So I hat is the estimated salary, alpha naught hat is the vertical intercept, and beta 1 hat is the slope of this line, and x is independent variable. So these dots, these circles, represents the actual observations of x and y, and this red line passing the red line straight line is the regression line. So this circle stands for male, and the red line is linear. This is linear regression for male. This blue line is also an estimated regression line, but this is for female. And here alpha naught star hat is the coefficient, this coefficient from here to there, and for the male the coefficient is from here to here, and this beta 2 is the slope of the regression, and beta 2 hat is the slope of the regression for the female teachers. So we see there are two regression lines. One is the red, this is for males, and this is for females. So if we compare both the regression lines, the only difference between the two is the difference in the intercept. The intercept of the male, that is alpha naught hat, is greater than alpha naught star hat, because this intercept is lower than this intercept, and the slope of the regression line is the same. These are parallel regressions. So one is this model, yi is equal to alpha naught plus beta 1 xi plus epsilon I. This is for male, and this one is for females. So the only difference between the two regression is that of the intercept or the constant. Rest of the model is the same, because the slope, that is beta 1 and beta 2 hat, are the same. Let us assume that beta 1 is equal to beta 2, which means that same slope but different constant between y and x. So the first model is yi is equal to alpha naught plus alpha naught prime di plus beta 1 xi plus epsilon I. And if we assume that beta 1 is not equal to beta 2, then it means that the slope is different and the constant is also different between y and x. Then we have this model, yi is equal to alpha naught plus alpha naught prime di plus beta 1 xi plus beta 1 prime di xi plus epsilon I, where yi is the annual salary and xi is the years of teaching experience. The dummy di is equal to 1 if the respondent is male, and 0 otherwise, that is 0 is the female. And we also take female as a control variable at the base category. If you look at this, there are two regressions here. Again, this red one is for male, we just discussed it a while ago, and this one is for female, this blue one. And if we sum up all the observations, and then this is the this green line is the whole sample, and y hat is alpha naught star hat plus beta 1 star hat x. So this is the sample for the overall, this is the regression line for the overall sample, which includes both male and female. So what difference do you see between these three different regression lines? Both the regression for female and male, they are parallel. The only difference is between the intercepts, but the overall regression line, the slope is the intercept is almost the same as that for the male, but the slope of the overall regression, the overall sample, is less than that of the male. Again, these are 25 observation. This D1 is for female and D2 is equal to 1 for male. This is annual salary, and these are the years of teaching experience. So if we sum up D1 and D2, then this is equal to 1. Again, this is the sum of this, and this is equal to 1. And we can write D1 is equal to 1 minus D2. Similarly, D2 is equal to 1 minus D1. So each dummy identify two different categories, but when sum up two dummies, it cannot identify which is male or female. So we must be very careful. So if we introduce two dummy variables in one model to identify two categories of the qualitative variables, such as yi is equal to alpha naught plus alpha naught prime d1i plus alpha naught double prime d2i plus b1xi plus epsilon I, where d1i is equal to 1 if male and 0 otherwise, and d2i is equal to 1 if female and 0 otherwise. This model cannot be estimated. Why? Because there will be a problem of perfect multicollinearity when we include both d1 and d2 in this model. Therefore, because d1 is equal to 1 minus d2, or d2 is equal to 1 minus d1, or d1 plus d2 is equal to 1. So there is perfect collinearity between these two dummy variables. So this problem in econometrics is called as dummy variable trap or multicollinearity trap. So in order to avoid this, if there are m categories, we will use m minus 1 dummy variables. Otherwise, the model will not be cannot be estimated. So using two dummy variables to identify two different qualitative categories in one model will fall into the trap of perfect multicollinearity or dummy variable trap. So the general rule to avoid the multicollinearity is, if a qualitative variable has m categories, we will introduce only m minus 1 dummy variables, so that we could avoid the dummy variable trap or the trap of perfect multicollinearity. Suppose, for example, we have these categories and they are m categories in age, so then we will use m minus 1 dummy variables. When a category is assigned the value of 0, this category is called a control category or an omitted group. Now consider different intercepts of two groups. Model 1. In this model, di is equal to 1 if male and 0 otherwise, that is female. Now we will measure the estimated result for two groups. For male, yi hat is equal to alpha naught plus alpha naught prime hat di plus beta 1 hat x, where di is equal to 1, and for female this will be equal to 0, so it will be yi hat is equal to alpha naught hat plus beta 1 hat xi, and here di is equal to 0. In order to test whether there is any difference in the relationships between two categories, we will compare these two models. One is this and one is this, and we will check the t value of this dummy variable. If t statistic is significant in alpha naught prime hat, there is difference in the constant term, and it implies same beta I hat means two categories of x have the same relationship with y, that is slope is the same. The null hypothesis is alpha naught prime is equal to 0. Alternative is alpha naught prime is either greater than 0 or not equal to 0. So the appropriate test is the t-test on alpha naught prime hat, and we will compare t computed with the t tabulated, and if t tabulated is greater than if t computed is greater than t tabulated, then it implies that we will reject h naught, and we will conclude that alpha naught prime hat is equal to 0. So y hat is equal to alpha naught hat plus alpha naught prime hat d plus beta 1 x1 hat, beta 1 hat xi plus beta 1 prime hat dx. Now we will check this. So this part is testing the difference of intercept, and we will also check this test of this beta 1 hat prime beta 1 prime hat. This part is testing the difference of slope in two categories. So if this is significant, then it means that the two slopes are different. If this one is not significant, then it means that the two regressions are parallel. Here is the computer software output. Separate example for female and male. This is for female, and this one is for male. So these are 13 observations, these are 12 observations. Here this is constant and it is significant. Here this is constant, coefficient of constant and significant. This is the years as an independent variable, significant. This is also years of experience, teaching experience, and this is also significant. Now the two regression results performed differently in slope and intercept. That is, this slope is different than this and this constant is different than this. But are they really statistically different? We cannot answer from these two separate regression results unless we test with the F test. So set two different dummies for the example. Here this is D1 is equal to 1 for female in this, and here D2 is, male is equal to 1 in this example. So this is the estimated regression, and this is the constant, and this is the coefficient of dummy variable. This is the constant, this is the coefficient of dummy variable. This is positive and this one is negative, but this is not significant and this is not significant. The two dummies are not significant and the separate examples. So this will be equal to 16.656 if the dummy variable were significant. Then this will be equal to this. This is the whole sample regression output. Cell is the dependent variable, and years of experience is the explanatory variable, and this is the coefficient of the experience, teaching experience. This is standard error, this is the t statistic, and this is the p-value, and the adjusted R-square is almost 61% or 0.61. This is the adjusted R-square, standard error of regression, sum of squared residual, log likelihood, Durbin-Watson, and so on. And this is the F test. So the overall regression is regression equation or regression model is significant. So yi hat is equal to alpha naught hat plus beta 1 hat xi hat. So this is 17.095 plus this is slope, and this is when we use dummy for a female as 1, and we also use the interaction term of the dummy with the ears. So let us see. Now this is the model, and the coefficient is equal to this, and this is the slope 1.7335, and for female this is for male. Since this dummy 1 is 1 for female, so this is for male. This is the male regression, and this one is for female. So you see there are two different, these coefficients are different, and even these slopes are different. But this one is equal to 0 and this one is also equal to 0, so we have this. And in this example, this is the eViews output, and here we are using D2 is equal to 1 for male and 0 otherwise, and here is this equation for female, 16.255 plus 1.677, this is slope, and this one is for male. Again this is equal to 0 and this is equal to 0, so we have 16.255 and 1.655. This coefficient is equal to 0 and this coefficient is equal to 0, so we have the same. There is no difference between the regression equation of male and female, because this dummy is not significant and this dummy is also not significant. So it means there is no difference in the intercept and there is no difference in the slope. Sometimes you have one qualitative variable with more than two categories. Say for example, education category may be high school, college, and maybe higher than that or less than that. So let us suppose our dependent variable is healthcare, and this is a constant, and this is the D2 is equal to 1 if high school education, 0 otherwise. This is D3 is equal to 1 if college education and 0 otherwise, and this is the quantitative variable income, its coefficient. This is epsilon, and this is x, and this one is y. So let us compare these various regressions. So we had this one, D2 is equal to 1, this is the regression with high school education, and this is the regression line with college education, and this one is the regression with the less than high school education. So you see the slope are the same, but there is difference in the intercept. This is the intercept of those with less than high school education. This is alpha naught prime hat. This is the intercept of those with high school education, and this is the intercept of those with college education. So these three regressions are parallel, but there is only difference in the intercept. And this is the data. These are observation for y, these are observation for x. D2 is equal to 1, and here D3 is equal to 1. So there are three categories, so we use two dummies. And this is the regression. We are using two dummies, and this is variable y, this is constant, this is x, this is D2, and this is D3. So if you look at the t values, that is t statistics, so the coefficient of the constant is significant because its p value is less than 0.05. The coefficient of x is also significant because its t value is 11.73 and its p value is 0.000, but the coefficient of these two dummies are not significant. So it means that there is no difference in the intercept of these three categories. And less than high school regression is this. For high school, this is the regression, and for college education, this is the regression. So if we simplify, we get this. We get this because there is no difference in the coefficients of the dummy variables. So they are this regression equation and this regression equation and this regression equation is the same, because we have this one quantitative variable with many categories. An estimated model on three different ages medical care expenditures. So we have this model. One dummy is this: A1 is equal to 1 if 25 is less than age is less than 25, or 55 is greater than age is greater than 25 and 0 otherwise. Another dummy will be A2, that is equal to 1 if age is greater than 55, and the sum of A1 plus A2 is not equal to 0 because we have one other category, and that is less than 25. So then the estimated models are these. One is for age below 25, one is for age ranging between 25 and 55, and one is for age above 55. And H naught is that alpha naught prime is equal to 0, alpha naught double prime is equal to 0, and alternative is that alpha naught prime is not equal to 0, alpha naught double prime is not equal to 0. So if t calculated or t computed is greater than t tabulated, then we will reject this null hypothesis. Otherwise we will fail to reject this null hypothesis. Now these are the regression line of these three different categories. This is for age below 25, this is for age between 25 and 55, and this is for age greater than 55. So you see the only difference is in the intercept of the constant. One qualitative variable with many categories. Again, this time we have, say for example, 4 categories, but we use 3 dummy variables, right? And the estimated models are these. For 4 categories, we have 3 dummies for 4 categories. This is the base category, or the control group, or the omitted case, and these are here A3 head is a dummy, here A2 head is the dummy, and here A1 head is the dummy. So we may also compare these here: salary, and these are various dummies. D1 is equal to 1 if male, 0 otherwise, and then D2 is equal to 1 if white, 0 otherwise. So mean salary for black male teacher will be like this when both the dummies are equal to 0. And this is mean salary for black male teacher, so there is one dummy here. And then this is the mean salary for white female teacher, and this is the mean salary for white male teacher. So there are 4 categories. Different types of dummy regression. There are 4 different types of dummy regression. One is identical regression, one is parallel regression, one is concurrent regression, and one is dissimilar regression. Identical regression means when both the intercept and the slope are the same. Parallel regression means when the intercepts are the different but slope are the same. Concurrent means when intercept is the same but the slope of the regressions is different. And dissimilar regression means when both the coefficient and the slopes are different. So we can see there are 2 different periods. This example is from Gujarati book. So one is reconstruction period and one is post reconstruction period. So here both these regressions are identical, as A1 is equal to beta 1 and A0 is equal to beta 0. So the intercept are the same and the slope are the same, so the 2 regressions overlap each other and we call it identical regression. This is parallel regression. The intercepts are the different. A0 is not equal to B0, but A1 is equal to beta 1. So slope are the same but intercepts are not the same, so these are called parallel regressions. This is called concurrent regressions. Intercept is the same but slope of this line is greater than the slope of this regression line. So this is called concurrent regression, in which A0 is equal to beta 0, that is the 2 intercepts are equal, but the slope of A1 is not equal to the slope of B1. This slope is less than this slope. So this is called concurrent regression and this is called dissimilar regression. Here neither the intercepts are equal nor the slopes are equal. So this kind of regressions are called dissimilar regressions. Interactive effects between 2 qualitative variables. Suppose we have this model and D1 is equal to 1 for female and 0 otherwise. D2 is equal for college graduate and 0 otherwise. So interaction effect can be like this. We will multiply D1 times D2. So if this coefficient is significant, then it means that there is interaction effect. If this is insignificant, then it means there is no interaction effect. So alpha naught prime means different effect of being a female. Alpha naught double prime means different effect of being a college graduate, and alpha naught triple prime means different effect of being a female with college graduate. A concurrent model or covariance or slope shift model. The example is, how can we test the hypothesis that the gasoline spending is different between a new car and a used car? Let us assume that at the beginning mile there is no difference between the used and the new car, but when we increase the speed with time, then the slope are not the same. The gasoline spending for the used car is higher than the gasoline spending for the new car, because the new car may be consuming less gasoline as compared to the used. Originally or basically their consumption is the same, but as the distance increases or the speed decreases, then the used car spends more gasoline as compared to the new car. So this is a kind of concurrent regression. Okay, here in this model we have multiplicative dummy variable and the estimated relation are like this. You can follow it. Compare this for the new car and the used car. So this is the hypothesis testing for the various coefficient, and the rule is that if t computed is greater than the t tabulated, then we reject H0. These are the data for y, x and dummy, and this is the multiplicative dummy with the x, which is equal to z1. So shift in both intercept and slope, and these are like estimating season effects, and that is E is the electricity consumption and T is the temperature. To capture effect of seasonal factors, these 3 dummy variables are used. There are 4 seasons, So D1 is equal to 1 if winter, 0 otherwise. D2 is equal to spring, 0 otherwise. D3 is equal to summer otherwise. And there is one more category, and that is fall. So this is the base category, or the omitted group, or the control group. So there are 4 categories, so we will use 3 dummy for 4 categories. So that is called control group. The estimated model for fall is this. This is the base category. This is for winter. This is for summer, and this one is for this one is for spring, and this one is for summer. So these are the various regression for the 4 different seasons. This is the omitted category, or the base category, the control group. This is for winter, this is for spring, and this is for summer. In summer, the intercept is much higher. The cost of electricity spending is much higher as compared to spring and winter and so on. So this is estimating seasonal effects. Also consider the slope in different seasons. This is the model. So the full general specification is this, and then we can also use quarterly effect is the same as a seasonal effect. D1 is equal to 1 if first quarter, 0 otherwise. D2 is equal to second quarter, 0 otherwise. D3 is equal to 1 for third quarter and 0 otherwise. And for the fourth quarter, it is a control group or the base category. And this is the output in eViews that we can define dummy. And it means set the seasonal dummy equal to 1 if there is a first quarter and 0 otherwise. So you can do like this. These are how various dummies are created. One for the first quarter, then one for the second quarter, then one for the third quarter, and this is one for the fourth quarter. So when all these are 0, it means automatically that this is the fourth quarter. Structural test based on dummy variables. Basic model is this: yt is equal to alpha naught plus beta 1 xt plus epsilon t, and let us suppose this is the time period ranging from 1960 to 1989, and there is one point 1974 here. So we can use dummy variable d1 is equal to 1 for the period 1974 onward, this period, and 0 otherwise, which is this period. So to test whether the structures of the two periods are different, the specification must assume that alpha star is equal to alpha naught plus alpha naught prime d, and beta star is equal to beta 1 plus beta 1 prime d, and dummy regression is like this. So we will use the Chow test on unemployment rate, capacity utilization rate, and here is the constant and the capacity utilization, the adjusted R square, the F test, the residual sum of square for the restricted model, and this is another one for the first period. So then this is RSS1, this is RSS2. So this is for the entire period, this is for the period 60 to 73, and this is for the period 74 and above. So we can use this test. H0 is no structural change, H1 is there is structural change. For the unrestricted model, the residual sum of square is equal to residual sum of square of period 1 plus RSS2, so it is equal to 7.98, and the F test value is equal to 14.9. We put all these values in the formula, and F calculated is F tabulated is 5.53. So since the F computed is greater than the F tabulated, so we reject the null, and we say that there is structural change in the model, and the two time periods are not the same. Using the dummy variable to identify the structural change, the unemployment rate, capacity utilization rate. So one sample is from 1960 to 1989, and this is dt is equal to 1 for the period 1974 to 1980 and 0 for the period before 1974. So unemployment, estimated unemployment is equal to 19.6 plus 11.0 dt minus 0.175 capacity utilization rate minus 0.121 the multiplication of dt with the capacity utilization rate. This is the adjusted R-square, this is the standard error estimate, and this is equal to 0.554. this is f, that is 72.2, and this observation number of observation is 30. So the estimated regression of 1960 to 1973 unemployment is this, that is 19.6 minus 0.175 cap, and this is for the estimated period 1974 and above, and this is equal to 30.6 minus 0.296 capacity utilization, and here is this is the observed data, this is the multiplicative term, and let me see. Now the basic model becomes this: yt is equal to alpha naught plus alpha naught prime d plus beta 1 xt plus beta 1 prime d times xt plus epsilon t, and so on. So we'll test this on beta 1 hat prime is equal to 0. So the estimated models are, this is 1 for 74, 1 and onward. This is the model, and prior to 1974 we have this, and this is the data. This is generate dummy 1 for sample 1970 to 1980, and then generate dummy 0 for sample 1981-91. This can easily be done in eViews. So we have this model. This is the estimated for 1970 to 1980 when d is equal to 1, and this is for 1981 to 1991 when d is equal to 0. So the dummy regression results are this, and this is for 70 to 80, and this is for 81 to 90. So we have this, and we have this, and this is 70. This is for 1970 to 91. This is the entire period, and this is for 70 to 80, and this is for 81 to 91. So you can compare all these values. This coefficient is different than this, and this constant is different from this and this. Here is the output. Only consider the difference in intercept, and this is not significant. This is not significant, so the coefficient of dummy is not significant. So this will be equal to 0. So we have this and this. This is whether intercept and slope both change. So in this case, yes, both are different. This one is significant, and this one is also significant. This is the interaction coefficient, and this is the dummy coefficient, and both of them t statistics are absolute t statistics are greater than 2, and their p values are less than 0.05. So these are significant. So it means that the slope and the intercept are both different. So we have this. The use of dummy variable in the pool data. That is the time series plus cross section, and here we have for each form run the separate regression. So we have this, and here this is the null hypothesis, and then we use the dummy variable. So if t computed is greater than t tabulated, then we will reject H0. Again, in this model you see If T computed is greater than T tabulated, then we reject H0. Similarly for this, if T computed is greater than T tabulated, then we will reject H0. And Chow test can also be used as structural stability test using dummy variables approach. H0 is no structural change, H1 is yes. So the procedure is like this: generate dummy variable D1 is equal to 0 for the period 1946 up to 1954, and D1 is equal to 1 for the period from 1955 up to 1963, or D1 is equal to 1 for the period 1946 up to 1954, and D2 is equal to 0 for 1955 till 1963. So we can generate like this. So dummy is equal to 1 for this period. Here is the sample, and the 0 1 is here for this sample. 1946-51 the dummy is 0, and for 1955 to 1963 the dummy is equal to 1. So here are the dummy values, and this is the output using the dummy variable to identify the structural instability. So we should look at this dummy coefficient and its p value and t value. So this is not significant. So this is a generate a dummy series dummy. So we will have to check this t statistic. If this is significant, we will reject the null, and if it is insignificant, then we will fail to reject the null hypothesis. This is the equation specification. Saving is the dependent variable, C is the constant, dummy, and then we have income as quantitative variable, and this is the interaction between the dummy and income, and this is for the overall sample, and here is the output. Now the dummy, this t statistic is significant, and this interaction effect is significant. So there is intercept change as well as there is slope change, because both of them are significant. So read the estimated results from the dummy regressions for the period 1946 up to 1954. The saving estimated saving equation is given like this: minus 0.2662 plus 0.0470 income, and this is for the period 1955 up to 1963, and this is the estimated saving equation, and finally we get this. So you see, this and this is not equal, this and this is not equal. So this is how we can use a dummy variable for structural changes, or the Chow test for structural changes. Ladies and gentlemen, today's my video's lecture was about using dummy variables as independent, the use of dummy variables as independent variables in the regression, and there are different implications of using dummies in the regression model. On the right hand side, there are policy implications. We can use them in cross-sectional data, we can use them in time series data, and we can use them in panel data. So if you like this video, you can share this with your friends, with your colleagues, with your students. And ladies and gentlemen, don't forget to subscribe to my channel, and don't forget to click on bell icon so that you can get notification about my future videos. Thank you and have a good afternoon.